Good afternoon, class. Today we are going to continue on with Chapter 6. In Chapter 6, Part 1, we talked about how to name compounds using metals found in Group 1 and Group 2 on the periodic table, paired with nonmetals from the right-hand side of the periodic table. If you will recall, metals from Group 1 on the periodic table form cations with charges of +1. Metals from Group 2 on the periodic table form cations with charges of +2. And nonmetals form anions with various negative charges depending on their location on the periodic table. Well, today we're going to talk about a very special class of metals called transition metals. Transition metals are special because they can form two or more positive ions depending on the situation they're in. Since they may form more than one charge, when we name compounds containing these special elements, we must have a way to tell the person coming after us which metal we are referring to. For example, you will notice here that copper can form two cations, copper +1 and copper +2. Iron can also form two cations, iron +2 and iron +3. Lead, another special metal, can form a charge of +2 or +4, again depending on the situation. Chromium can form a charge of +2 or +3. You do not need to memorize these charges. If the metal has already been placed for you with its nonmetal in the form of a compound, such as an example 4, MnF2, you can determine the charge on that transition metal by looking at the charge on the anion. If the compound is instead given to you in its name form, i.e. if someone has told you the name of the compound, you can determine the charge on that metal from its name. I will show you how to do both. To name a compound, to take the formula and write the name, we use the charge on the anion and charge balance to calculate the charge on the metal ion. For example, MnF2. Manganese is a transition metal, meaning it can form more than one charge, so we don't necessarily know the charge on the manganese. However, the second element in this is fluorine. We know that fluorine always forms a charge of -1. It is in group 17 or 7A on your periodic table. All elements in that group form a charge of -1. There are two fluorines. Each one has a charge of -1. So we have two negatives. Since the compound must be overall neutral, the manganese must have a positive charge that is equal and opposite to the negative charge on the fluorine. There is only one manganese in this compound. 1. Therefore, those positives must all be on that manganese. Since there are two negatives, there must be two positives on this manganese. Therefore, the charge on the manganese is +2. Charge on the fluorine is -1. To name the compound, when you have a transition metal, you use the charge. And what we do with the charge is we place it in a Roman numeral form. So let me erase this here. We now know that it is manganese +2, fluorine -1. So the name of this compound is manganese. We place the charge in Roman numeral form, 2, in parentheses, space, the name of the nonmetal, changing the end to "ide." So just like before, we still have the name of the metal unchanged, the name of the nonmetal with the ending changed to "ide." Only difference here is that now we add in the charge on the transition metal in Roman numeral form. So for example, we have chromium +2 and chromium +3. We have lead +2, lead +4. You can see the Roman numerals here. If you are unfamiliar with the Roman numeral system, we'll do a quick review. Capital letter I is Roman numeral 1. II is Roman numeral 2, III is Roman numeral 3, IV is Roman numeral 4, V is Roman numeral 5, VI is Roman numeral 6. You shouldn't have to go above 6 in this section. Okay, so guide to naming ionic compounds with variable charge metals. Variable charge metals being fancy speak for transition metals. Step 1. Determine the charge of the cation by looking at the anion. None of the anions that we use have variable charges, so you will always know the charge on the anion. For example, all of the 7A's, the halogens, fluorine, chlorine, bromine, iodine, they all form a -1. All of the 6A's or 16's, oxygen, sulfur, they form a -2. All of your 5A's or 15's, like nitrogen and phosphorus, those form a -3. So again, the charge on the anion doesn't change. Step 2, name the cation by its element name. This has not changed from our previous method. The name of the metal doesn't change. The only difference is that we now use a Roman numeral in parentheses to indicate the charge on this metal. Step 3, name the anion by using the first element of its element name followed by "ide." Again, this has not changed from our previous step. We always name the anion by its element name and changing the ending to "ide." Step 4, of course, the cation is first, the metal is always first, followed by the name for the anion. So let's try some examples. Example 5, name the ionic compound FeCl2. If we look at our periodic table, we will see that Fe stands for iron. Fe is on the short fat part of the periodic table. It is a transition metal, so we don't know the charge on it. Chlorine, on the other hand, is our anion. Chlorine comes from the upper right-hand corner of the periodic table. It is in group 7A or 17. Therefore, we know that its charge is always going to be a -1. There are 2 chlorines for a total of -2. We know that the compound must be overall neutral. Therefore, the charge on the iron must be equal and opposite to the charge on the chlorine, 1, 2. There is only 1 iron, so both of those positives must be on the iron. To name this compound, we keep the name of the metal, iron. We put its charge in parentheses in Roman numerals, II, iron 2. We take the name of the anion, the covalent compound, and we keep it, but we change the ending to "ide." So instead of chlorine, we have chloride. So the name of this compound is iron 2 chloride. That tells the person who maybe doesn't know which iron chloride you meant that you are referring to an iron with a charge of +2 and 2 chlorines. How about the next compound? We have SN, which stands for tin, SN, and we have oxygen. We have 2 oxygens. If we look at our periodic table, we will see that oxygen falls in group 6A or 16. Each oxygen has a charge of 2-. There are 2 oxygens, so we have total 4 negative charges, 2 from each oxygen. This must be overall neutral, so we must have 4 positives to balance our 4 negatives. Since there is only 1 tin, all 4 of those positives must fall upon that 1 tin. So the name of our compound is tin 4 oxide. Again, keeping the anion the same, but replacing the ending with "ide." Let's try another one. How about iron 3 chloride? Now we're going to take the name and go to the formula. Before we had the formula and we wrote the name. The name, iron 3, tells us that the iron must have a charge of +3. Chloride tells us that we are looking at an anion from chlorine, and chlorine always has a charge of -1. These must be overall neutral. At the moment, we have 3 pluses on our iron and only 1 minus on our chlorine. So right now, we have 2 positives left over. Well, what can we do about that? Add another chlorine. Now we have another negative. That negative and that positive cancel out. Still have a positive left over. What can we do? Add another chlorine. That chlorine now cancels with that positive, and we are overall neutral. So the formula for this compound is FeCl3. 3 chlorines, 1 iron. Let's try a few more. Write the chemical formulas for the following compounds. Nickel 2 sulfide. If we look at our periodic table, we will see that the symbol for nickel is Ni, and the Roman numeral 2 tells us it has a charge of +2. Sulfide comes from sulfur, which is in group 16, or 6A, meaning it has a charge of -2. So right now we have 2 pluses and 2 minuses. With a 1-to-1 relationship, these two things cancel out. So therefore we have 1 nickel for every 1 sulfur. And the formula for this is NiS. Let's try another one. Zinc chloride. Chloride is from chlorine, which is in group 17 and has a charge of -1. Zinc, Zn, we don't know the charge on that. There is no Roman numeral written in parentheses. Therefore, for this metal, since it is a transition metal, and there is no Roman numeral written, we can assume that it is a +1. A +1. There is 1 zinc and 1 chlorine. +1, -1. Those two balance each other out, and the formula is ZnCl. If there was a Roman numeral written after the zinc, then you would know that the charge was something other than +1. Let's look at another one. Iron 3 oxide. Iron, as we said in a previous example, has the symbol Fe. The 3 tells you that it has a +3 charge on it. Oxide tells you that you are looking at oxygen. Oxygen comes from group 16 or 6A and has a charge of -2. We wish to make these things balance out. In order to do this, we would have to figure out how many pluses and how many minuses. A +3 and a -2, the least common denominator for this would be 6. So if we multiplied our +3 by 2, you would get +6. And if you multiplied your -2 by 3, you would get -6. So the formula for this would be Fe2O3. Again, if we look at making sure our charge is balanced, if the iron is a +3 and there are 2 of them, we have 1, 2, 3, 4, 5, 6. 6 positives. Oxygen is a -2 and there are 3 of them. 1, 2, 3 of them. Therefore, these balance out. +6, -6. So the formula is Fe2O3. Finally, we have another class of compounds called polyatomic ions. Polyatomic ions are groups of atoms with an overall charge. So instead of a cation and an anion, each consisting of a single atom, as in our previous examples, we have groups of atoms that have a charge. They typically consist of nonmetals, such as phosphorus, sulfur, carbon, nitrogen, and oxygen. They generally have negative charges, 1, 2, or -3. The only exception to the negative charge rule is something called ammonium, which is NH4. It has a charge of +1. In table 6.7, you will see the names and formulas of some common polyatomic ions. These are important. You should know these polyatomic ions as we will be using them frequently throughout the semester. And who knows, they may show up on a midterm or a final exam. So you should know the names of the common polyatomic ions. If you look at this table closely, you might notice some patterns. Many of the common polyatomic ions have names that end in -ate. Such as sulfate, phosphate, and nitrate. When a polyatomic ion exists as part of a family, if its related ion has 1 less oxygen, its name ends in -ite. For example, sulfate has the formula SO4 and a -2 charge. Sulfite has 3 oxygens, SO3, with the same -2 charge. Phosphate has a PO4 formula with a charge of -3. Phosphite has 3 oxygens instead of 4, PO3, with the same -3 charge. Nitrate has a -1 charge. Nitrate has the formula NO3. Nitrite has the formula NO2 with the same -1 charge. So you may notice a pattern here. All of the atoms, or polyatomic ions rather, within a family have the same charge. For example, all of the chlorine family, perchlorate, chlorate, chlorate, and hypochlorite, all have a charge of -1. The only difference is in the number of oxygens. If you look at the sulfate family, they all have a charge, let's not talk about these ones with hydrogen in them yet. We will talk about them, but not yet. For right now, I'm referring to sulfate and sulfite. They both have a charge of -2, but one has one less oxygen. Same thing with the phosphates. Again, we're going to talk about the ones with hydrogen here in a minute, but for now, let's just look at the ones without the hydrogens. PO4 3-, PO3 3-. Both have a 3- charge. Same thing with nitrate and nitrate. Both have a -1 charge, but one has one more oxygen than the other. So when you're looking at the names of these ions and you're thinking about memorizing your common polyatomic ions, I strongly recommend that rather than memorizing this whole list, if you take the pairs, nitrate, nitrite, chlorate, chlorite, sulfate, sulfite, phosphate, phosphite. Memorize one in each pair, and then just remember that the ite has one less oxygen and the exact same charge. Now, we are going to talk in a minute about what happens for those that have hydrogens on them. We will get there. Before I get there, though, there are a few exceptions to the 8-ite rule. Cyanide and hydroxide, and of course ammonium, do not end in 8. Now, on to the ones that do have hydrogen. If you add a hydrogen to a polyatomic ion, you add +1 to its charge and the word hydrogen to its name. For example, carbonate is CO3 with a 2- charge. If you add a hydrogen to this, its charge goes up by +1, so instead of -2, it is now -1. And its name is now hydrogen carbonate. So anytime you add a hydrogen to a polyatomic ion, the name stays the same. You add hydrogen to it in front of the original name, and you add a +1 to its charge. Again, these are really important, and you should know the names in this table of these common polyatomic ions. So, how do we write the formula for an ionic compound if it has a polyatomic ion? Well, we still have to use the same rules of charge balance as those for simple ionic compounds. For example, magnesium nitrate. You have a magnesium ion and a nitrate ion. Magnesium, as we've learned before, is a charge of +2. Nitrate, as we just learned a few minutes ago, is NO3 with a charge of -1. At the moment, we have 2 pluses on our magnesium, 1 negative on our nitrate. We need these to balance out, but we're not balanced yet. So what do? Well, just like in previous examples, we must add another nitrate with another -1 charge. Now my charges are balanced out. 1 magnesium to 2 nitrates. When we write the formula for this, MgNO3, we need to indicate that there are 2 nitrates. However, if I simply write the 2 here, what does that look like? Well, to me, that looks like 32 oxygens, not 2 nitrates. The simple way to solve this is to put parentheses around your polyatomic ion. That tells the person that there are 2 nitrates, not 32 oxygens. So again, when you're using a polyatomic ion, if you need more than one of them to balance your charges, you must write parentheses around the polyatomic ion and indicate the number of polyatomics by writing a subscript outside of those parentheses. So let's try another example. Example 9 says, write the formula for sodium phosphate. If we look on the periodic table, the symbol for sodium is Na. It is in group 1. It has a charge of +1. Phosphate, PO4, PO4. And if we look back to our previous table of polyatomic ions, you will see that the phosphate family have charges of -3. Okay, so let's go back. Charge of -3, we have PO4, 3 minus. Just like before, we need these to balance. Right now we have a +1 and we have 3 minuses. So at the moment we're not balanced, right? What do we need to do? Well, we need to add 2 more positives. Adding 2 more positives means adding 2 more sodiums. So our formula is Na3PO4. Now, why did I not write parentheses around my sodium when I put the 3 there? Well, we don't need to, right? Just like in previous examples, we only have 1 sodium, so that 3 must refer to the sodium, rather than having to worry about it referring just to the letter A. So for the formula for this, it is Na3PO4. How about a couple more examples? Let's see what we got here. Number 10. It says, when naming ionic compounds containing polyatomic ions, we first write the positive ion, which has been true so far of all of the examples we've done, whether it's polyatomic, simple metals, or transition metals. We always write the positive ion first, which is usually a metal, except in the case of ammonium. We write the name of the polyatomic ion second. Recognizing a polyatomic ion in a chemical formula will help you to name it correctly. As with other ionic compounds, we do not need any prefixes. The easy way to recognize that you have a polyatomic is to separate out your metal from everything else. If you notice that everything coming after the metal has more than one element, in this case, and this case, we then know that we have a polyatomic ion to deal with. So let's name these compounds. Na. Na, if we look on the periodic table, is sodium. SO4. If you look at your table from the previous page, SO4 is sulfate. So we have sodium, sulfate. Sodium sulfate. How about the next one? Fe stands for iron. Fe stands for iron. Iron is a transition metal. Right? Iron is a transition metal. When we name something with a transition metal, we must indicate the charge. How can we do that? Well, our polyatomic here is PO4, which is phosphate. If we go back to the previous page and we look up phosphate on our table, we will see that the phosphate polyatomic ion has a charge of -3. -3. In order for this to be balanced, which it must be, 1, 2, 3, and neutral, that iron must have 3 positives to balance the 3 negatives. Since there is only 1 iron, all 3 of those positives must belong to that iron. So to name this compound, we have iron. We have a charge of +3, so we place the Roman numeral in parentheses, iron 3, phosphate. Shall we try another one? Al. If we look at our periodic table, Al stands for aluminum. Yes, aluminum. CO3. CO3. Again, if we look at the periodic table, I'm sorry, not the periodic table. If we go back to our previous table and we look up carbonate, CO3 has a charge of 2-. So we have a CO3, 2-. There are 3 of them for an overall -6. Aluminum, if we look at where it is on the periodic table, it is in group 13 or 3A. That, of course, means it has a +3. There are 2 of them, so it has a total of +6 charge, as it should. They are balanced. So the name of this compound is aluminum. We do not need the Roman numeral here because this is not a transition metal. Aluminum, the polyatomic is carbonate. This is aluminum carbonate. Again, aluminum is not a transition metal, therefore we do not have to tell anyone else what the charge is by using the Roman numeral. Okay, one last class of compounds that we're going to learn how to name. We call these molecular compounds or covalent compounds. The reason for this is that these are made up of two or more nonmetals. There are no metals anywhere in this compound. And instead of a metal donating an electron to a nonmetal, our two nonmetals share electrons. We call this a covalent bond. So we are going to practice naming covalent compounds, also known as molecular compounds. Molecular compounds have valence electrons that are shared by nonmetal atoms to achieve stability. Okay, I just want to make that very clear. Instead of having a transfer of electrons, we have a sharing of electrons. When naming a molecular or covalent compound, the first nonmetal that is in the formula is named by its element name. The second nonmetal is named using the first syllable with the ending changed to "ide." So just like before, except we have no metals now. If there are two or more atoms of an element, we use a prefix to indicate how many there must be. So let's take a look at our first example, NCl3. If you look at the periodic table, you will see that N is the symbol for the element nitrogen, Cl is the symbol for the element chlorine. So we are going to take the first nonmetal, named by its element name, which is nitrogen. We are going to take the second element and change the ending to "ide." However, if we have two or more atoms, we use a prefix. There are 3 chlorines, so if we look at the prefixes, 3 is tri. This is nitrogen trichloride. Okay, let's try another one. We have B2O3. We have 2 elements. If we look at the periodic table, we will see that B stands for boron and O stands for oxygen. So we have boron, but there are 2 of them. So if we look at our prefixes here, we have diboron. We have 3 oxygens, so that is tri. And then, of course, we change the oxygen to oxide. So again, there are no charges on these atoms. We are not balancing anything. We are simply taking the number within the formula and using that to name the compound. How about another one? This time, let's write the formula for diphosphorus pentoxide. If we look at our table from before, di stands for 2 and penta is for 5. So going back here, we're going to have 2 of whatever this is and 5 of whatever this is. If we look at the periodic table, we will see that the symbol for phosphorus is a capital P. There are 2 of them. Oxide is for oxygen, and there are 5 of them, so the formula is P2O5. How do we tell the difference between all of these compounds? How do we know if it's ionic or covalent or polyatomic? Well, a compound is usually ionic if the first element in the formula or the name is a metal, or the polyatomic ion ammonium, which again is the only polyatomic ion with a positive charge. So you're looking for something with a positive charge, typically a metal or ammonium. So for example, K2O, K is a metal, potassium, therefore the compound is ionic. A compound is covalent if the first element in the formula is a nonmetal. For example, N2O. N is nitrogen, which is a nonmetal. Therefore, the compound is covalent. Quick aside, how do we name that? Dinitrogen oxide? Okay, let's talk about something a little bit different. Let's talk about Lewis structures for molecules and polyatomic ions. A Lewis structure is a representation of a molecule in which the valence electrons of all the atoms are arranged to give octets. Octet means 8. So what we are looking for here is to see that all of the valence electrons on all of the atoms have 8, with a few exceptions. For example, hydrogen. Hydrogen only likes 2 valence electrons instead of 8. A hydrogen molecule, H2, forms as the atoms move closer and closer and closer. The positive charge on the nucleus attracts the electron, which is negatively charged, on the other atom. Eventually, when they get close enough, the two electrons are shared between the two nuclei. This sharing of electrons is called a covalent bond, and it is designed to give a noble gas arrangement to each hydrogen atom. The only noble gas that has less than 8 valence electrons is helium, and it is helium that hydrogen wants to be like. Molecules form when their energy is more stable than the individual atoms alone. So an H2 molecule, or hydrogen, is more stable than 2 individual hydrogen atoms. We use a Lewis structure, which is a drawing, to represent this. The shared electrons, or bonding pairs, are shown as 2 dots, or a single line between atoms. The non-bonding pairs, or lone pairs, are placed on the outside of the atoms. So in this drawing here, each one of these bonds represents 2 shared electrons between a hydrogen and the central nitrogen. These 2 dots on top of the nitrogen represent 2 electrons which are not participating in bonding. They belong solely to the nitrogen. They are not being shared. Let's try an example. A molecule is represented by a Lewis structure in which the valence electrons of all the atoms are arranged to give octets. Let's draw the electron dot formula for the fluorine molecule F2. Let's look at each fluorine atom. Fluorine is in group 17, or 7A, and has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. We represent these as dots around the fluorine. As we can see, neither fluorine has 8, so each fluorine shares one of its electrons with the other fluorine. That bond represents the 2 shared electrons. Now, this fluorine has 2, 4, 6, 8 electrons, and this fluorine has 2, 4, 6, 8 electrons. Everybody is happy. Therefore, the Lewis structure of fluorine is drawn with a single bond between the 2 fluorines, and each one having 6 electrons that are not participating in the sharing. The elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist in this manner. We call them diatomic molecules. Di meaning 2, atomic atoms. So 2 atoms. This is hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are important. They always exist in nature as H2, N2, O2, F2, Cl2, Br2, and I2. Diatomic molecules. The number of electrons a nonmetal atom shares and the number of bonds it forms are usually equal to the number of electrons it needs to achieve a stable electron configuration, which again, for most atoms is 8. There are a few exceptions like hydrogen, who are satisfied with less than 8, and there are also a few elements that prefer more than 8, but most of what we'll deal with are 8. So let's try another one. Let's draw the electron dot formula or Lewis structure for methane. We are going to draw the Lewis symbols for carbon and hydrogen first, and then we are going to see if we can get everybody happy. So carbon on the periodic table is in group 4A or 14. It has 4 valence electrons. As we just said, each hydrogen has 1 valence electron. Okay. We want everybody to have 8, or except for hydrogen, of course, which only wants 2. In order for carbon to get 8, it only has 4. It needs someone to share 4 more electrons with it. So if each hydrogen shares its 1 with each carbon, Carbon will then have 1, 2, 3, 4, 5, 6, 7, 8. Each hydrogen, remember, only wants 2 to be like helium. Each hydrogen, if it gets 1 shared from from the carbon, has 2. 1, 2, 3, 4, 1, 2. Therefore, everybody's happy. So we can draw a line connecting each hydrogen to the carbon. So if we draw this over here to make it look a little neater, it looks like this. Again, each line represents 2 shared electrons between the 2 atoms. Shall we try another one? I need to erase this, get it out of my way a little bit here. Alright, let's draw the Lewis structure for PCl3, which is used in the preparation of pesticides. Step 1, determine how to arrange the atoms. There are some guidelines that will make this a little easier for you. Many times, if you have one of one type of element and multiples of another, the element that you only have one of goes in the center. For example, we just did methane with a carbon and 4 hydrogens. The carbon went in the middle. Here we have PCl3. The P is going to go in the middle with the 3 chlorines surrounding it. So again, if you have one of something and multiple of something else, the one that you only have one of often goes in the middle. If you don't have that situation, the least electronegative element goes in the center. The least electronegative. There is a table on D2L and also in your book that lists the electronegativity values if you're attempting to determine who is least electronegative. Although you might remember on the periodic table, the trend for electronegativity is that it increases up and to the right, with fluorine being the most electronegative element ever. The one thing for this, though, is that hydrogen is fairly low in electronegativity, but hydrogen is never the center. Never, ever, 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 ever in the center. It can only form one bond. So when you're determining who's in the center, never pick hydrogen. Okay, so we have PCl3. As we said, we're going to put the P in the middle. The chlorine's on the outside edge. Then we're going to draw in their electrons. Each chlorine has 7. Based on its location in the periodic table. So let's just draw these electrons in here. And then if we look at the periodic table, we see that phosphorus is in 5A. It has 5. 1, 2, 3, 4, 5. So as we can see, it needs 3 electrons to be shared in order to be happy. It has 2 on the top. If it shares with a chlorine, it now has 3, 4, 5, 6, 7, 8. So phosphorus would be happy. Each chlorine needs 1 electron, so it shares 1 with the phosphorus in exchange for phosphorus sharing 1. Now each chlorine has 8, and each phosphorus has 8. So we can draw the Lewis structure as 1, 2, 3 chlorines surrounding, 1 pair of electrons on the phosphorus that is not participating in the bonding, and 3 pairs for each chlorine that is not participating in the bonding. This is the Lewis structure of PCl3. Shall we name it? Is phosphorus a metal? Well, let's take a look at the periodic table. It's in the upper right-hand side. It's not a metal. So how would we name this? This is considered a covalent compound, right? We're sharing electrons. So we would name this as phosphorus trichloride. Phosphorus trichloride. That concludes Chapter 6, Part 2. Thank you for listening, and I hope to see you for Chapter 6, Part 3.